My name is Wiebke. Thanks, as I've been introduced. I come from a mechanical engineering background, so until about 4 years ago, I stayed away from codes, computers, algorithms. And I've just submitted in March, I just submitted my MSc in computer science, which I'm really proud of. It was probably one of the toughest achievements I've done. So I've got great appreciation. Thanks. Thank you. Applause before I've even started. So I've got great appreciation for the abundance of concepts, complexity, words, formulas, algorithms, even algorithm as a word being chucked at you when you're starting off and you've got very little idea of what it really means beyond the words on paper. So it's a 101 talk exactly because of that, because I felt from previous Indabas where I've been at, it's really nice to have one presentation where you leave and think, yes, I understood everything. So that's effectively my goal, is that everybody can leave this room at the end of today and say, yes, I understood everything. And ultimately, I'll rely on your assistance to help me do that. So you'll need to speak up if I don't make sense or if there are questions that remain. By quick show of hands, just so that I can get an idea of the audience, who's having their first in-depth introduction to machine learning at the IndabaX now? Cool, awesome, yay. Wonderful. I'll do a little bit about Engineers Without Borders now because it's not actually featuring in my talk. And one of my passion behind Engineers Without Borders is that I believe as engineers, but as designers in general. And I think as engineers, designers, and creators, and software engineers, artificial intelligence, machine learning technologists definitely fall into the category of designers and creators. I believe that we fundamentally have a responsibility to design for the people of this world, and not just for a small segment of the population, but for everybody. And a big part of our mission with Engineers Without Borders is to make sure that we provide access to engineering expertise and skills to South African community at large, but also to embed an idea of what it means to design for people already in the university curriculum and at students. So if you've got any interest about speaking about designing for people, creating for people, I'm always up for those conversations too. I normally like walking around, so I'll probably just pendulate 90 degrees between the left side and the right side. Great, so to start with, I've got some questions for you. And questions are, why are you here today? Why did you choose to come to the Indaba? What are your goals? What results are you hoping to achieve, and what does success look like? Is there anybody who's willing to share an answer to any of those? I've got a lot of questions in this presentation. I'm hoping for it to be interactive. So this is a warm-up round. They get harder. If you answer now, you don't have to answer later. Yes? You'll have to speak up, stand up, and speak loudly.
I haven't worked much with unsupervised learning, so I'm excited to see what can be done, and excited to see what's in store for us here today.
Hi, so I'm a master's student, and while I've dabbled in unsupervised learning and supervised learning, as I've discovered very quickly at this conference, there is a wealth of knowledge that you don't know. So the reason why I'm attending this is basically there's always something to learn, and even if maybe 10% of it is applicable to me for my master's studies or something interesting that I'm looking to apply, there's always something to learn. That's why I'm here.
Great. So I'll share with you why I'm here, but also a framework that I find is really helpful, has been really helpful for my personal learning. So I just have a very small, very easy framework that I use personally. So it's effectively a four-tier approach, and I found it helpful when you're learning a new concept, is that ultimately the first time you encounter information, it always seems like there's so much and you don't quite know how to structure it in your mind. And what I've started doing is looking at from results to problems to tasks to skills. So effectively, what are the results that you're trying to, like that field of information that you're dealing with is ultimately trying to achieve? What are the problems that need to be solved to achieve those results? Which tasks need to be done to achieve the problems? And then ultimately, which skills are required as small little individual packets of things to learn? And again, where it's helpful is I find when you're starting off, quite often I'd get confused between the skills and the results and the problems and the tasks. And you're kind of trying to learn all of it together at the same time. So for me, if I speak about this particular presentation, the results I want to achieve are twofold. I want to share an application of a learning framework that I use with you. And I want to instill an appreciation of unsupervised machine learning in you. Then from a problem perspective, what are the problems I need to solve in order to get those results? I need to capture your attention. If I don't capture your attention, I've lost from the beginning. And I need to figure out how to distill complex technical concepts with simplicity, because if I don't do that, then I'll have lost. Some of the tasks I need to do is I needed to prepare a presentation, and I need to deliver a lecture. And finally, in terms of skills, I need to have the skill of knowing how to project my voice and how to use PowerPoint. Thank goodness PowerPoint was very easy, so there was no challenge with that. So in terms of what this session is going to be about is I'll first, going back to fundamentals, contextualize machine learning in the broader field of AI, or actually AI and data science, then recap some of the machine learning fundamentals, do an introduction to unsupervised machine learning, then we'll move to cluster analysis and going a bit deeper into cluster analysis. All in all, there's one formula, I think, in this whole presentation, so expect it to be high level and engaging rather than deep technical. Cluster analysis itself, and I guess a lot of application-based unsupervised machine learning has got a lot of documentation online, a lot of videos online, and so you will be able to find that information yourself. I think this is really to help guide you where to look. So, so maybe in a bit of a personal perspective, I've spent the last 3 years, half in academia, actually maybe 6 years. So my career, half in academia, half in industry, half in nonprofit. It makes for 1.5 lives, which sometimes gets a bit too much. But I've often found it interesting. So I've experienced a lot of the hype of AI in the industry space. And I do think that a lot of the hype of AI trickles down into beginner-level machine learning, that we don't always really know what we're talking about when we speak about data science, AI, and machine learning. And so I found this visualization quite a nice way of thinking about it, is that in terms of AI, or let's call it traditional AI, you really have a number of different fields that people look at. So there's robotics, there's planning, there's computer vision, natural language processing, knowledge representation, and reasoning. And so effectively, if we quickly switch back to that results, problems, tasks, and skills framework, if we speak about computer vision, the result that we want to achieve with computer vision is to have a machine being able to see. The problems that they need to solve is how to take visual input and turn it into an output that is interpretable by humans. The tasks that need to be done would then relate to algorithms that need to be crunched. And the actual skills that we need on that level then might lead to something like parameter optimization or so on. On the data science side data science is much more the production of machine learning specifically. So you'll end up spending 80% of your time in data science building pipelines, testing and experimenting with different models. It's not necessarily always, so again, more in the industry space, it's about communicating your results. It's about making sense of the data, scaling it from a small academic scale. And again, in an academic setting, we're often quite happy to have a test case where we know it works in test case. Whether we can scale it for 10 million people to be used is not necessarily always our primary concern, whereas data science and industry looks for that. But machine learning ends up being the sliver in between data science and AI that is quite core it's a discipline of AI that is core to, or that is the pinnacle maybe of data science. So, okay, moving on to the next. I thought it was worth it recapping what algorithms are. And from the perspective that, again, starting off as a newbie, I read about algorithms a lot, and I really struggled to find a definition somewhere that made sense to me of what is an algorithm actually. So I thought a nice way of thinking of it is as the coffee algorithm. So any algorithm ultimately has an input, a process, if we've got an input and a desired output, there's a process that happens in the middle. That process is effectively what an algorithm does. So becomes an algorithm when we've got a machine doing it, but we can conceptualize it as a simple task that we might do as a human. So again, if we say an algorithm is a process that converts an input to an output, we could start with a bunch of coffee beans. The coffee beans then so how do we get from coffee beans to making a cup of coffee? involves a series of steps. It involves grinding the coffee granules, it involves adding hot water, it involves letting the coffee brew for a while, and eventually we've got our cup of coffee. Now, there are many, many different ways in how we can actually do this. So, okay, this is a bit of pseudocode, another language term. So pseudocode is human-readable code that helps us understand the high-level overview and concept of how an algorithm works. You can't feed that to a computer, but it does help you to understand the step-by-step process. So effectively, for making coffee, I'd say take coffee beans. I haven't specified how many coffee beans. I haven't specified if we take all coffee beans at once, or if we take coffee beans bag by bag, or bean by bean. Then we say for each bean, crunch the beans. Yeah, so effectively, if you think of coffee making as a process and saying these are the steps this is the algorithm required for making coffee, there are a whole bunch of variations that you can do in terms of how you grind the beans. Do you grind them all at once? Do you grind them in batches? Do you grind them really fine, or do you grind them quite coarsely? How long does it take to grind them? Are there certain ways of grinding that make it grind faster? So that starts speaking to what's the quality of your coffee granules? What's the quality of your data? In terms of adding hot water, you can choose to add the hot water at the beginning rather at the end. And so the same, if you start thinking of an algorithm, again, merely as a process that converts an input to an output, and if you start saying the millions of processes I act out every day in life, I find that they become a lot friendlier in terms of how you feel about it, because ultimately it means saying, how do I break that process down into understanding its different steps? And how do I start understanding which parts of it I can tune? Is there anybody who has a question still about what algorithms are or do? Because I think that's quite a fundamental thing to understand, and there might be some other people who've got alternative explanations if there's still a question mark. I can reframe it. You shouldn't leave this venue without knowing what an algorithm is. Everybody comfortable? Cool. Great, and so if we go to a definition of machine learning as a very simple one, it's a field of research that's concerned with programming computers to automate the process of converting observational data into an output that learns from the input data. So again, we're speaking process, which means there must be a whole bunch of algorithms involved. We've got input data that's observational. Probably have to qualify in that case. It doesn't have to be observational, as we learned this morning. So there are many approaches of generating data, so I don't know much about them. But yeah, for an introductory perspective, it's observational data into an output data, and we want to learn from the data. So if we're going back to our results, problems, tasks, and skills framework, what exactly does that mean? It means that the result that we want is ultimately, we want to predict an image category. We might want to identify anomalous behavior. We might want to group similar observations. That's the result that we want at the end of the day. The reason why it's important to remember, again, in the context of technology in the real world, we often get distracted by the beauty of the algorithm or the complexity of the algorithm or the difficulty to implement it. And we forget that all we needed was to predict the image category. And if we've got a monkey that's sitting there that can accurately predict for us, we don't need to have algorithms. If the monkey is faster than what our algorithms are, we have to ask ourselves, are we doing the best approach? So effectively, machine learning is a great set of tools that allows us to automate a lot of things, but we should always keep in mind what the ultimate result is that we want to achieve. Then the problems that we need to solve is, or one of the core problem is, how do we use previously captured data to make the best possible prediction? Or in other words, how do we build a good model? And again, there might be many different ways of solving that. And why do I like to think of it in terms of results, problems, tasks, and skills is because thinking of it in those high-level, simpler terms allows you to again get rid of the confusion and hopefully find the creativity, because maybe you've got a way of thinking about how to go about this that works for you and is uniquely creative, but if you're confused, you don't always get them. So the tasks that we need to do in order to be able to do this is we need to prepare our data input, we need to apply algorithms, and we need to evaluate the output. Effectively, that's all that it is. And then some of the skills that we need, the challenges would be is how do we select and weight features? How do we normalize our data? How do we set optimal parameters? And how do we choose appropriate metrics? And so effectively, as you're sitting in the talks, you start building up kind of what are the results, what are the skills that we need, how do we bring the results, the problems, the tasks, and the skills together. Then you can start building a complete mind space in your head of what it actually takes to build the skills that you need to become good at machine learning. Yeah, so I'll read what I said, because what I wrote, because sometimes that's nice. So ultimately, good results is what matters, not only applying sexy algorithms. And as beginners, we often get bogged down in applying creative algorithms and don't pay attention necessarily to the components that significantly influence predictive results. Yeah, and so I think in supervised machine learning, it's maybe less of a problem. In unsupervised machine learning, there have been a lot of studies that have shown that the novel, complex approaches that people have tried to kind of tweak here and tweak there actually don't necessarily outperform the standard if they were to be baselined well. In terms of language, here are 4 concepts, again, that I want to make sure that everybody's understood, because I think if you don't understand them, then following any subsequent talks and information about machine learning becomes quite tricky. So the first, training data. Training data are effectively is the input data that you use in order to, so that's your input observational data that you use in order to build your models. Features are predictors of the output. So the features are usually, or actually always, constructed from your training data, but they don't necessarily have to be the same. So if we've got, for example, a 256 pixel image, you might use principal component analysis or something similar to reduce it to only 6 features that are important in that particular instance. So features is that space of your input that you actually want to use for your model. Labels are the output variable of past observations that are associated with the input features. So if I know that, so again, let's take 256 pixels. Let's say we've reduced it down to 6 features. If I know those 6 features represent a flower, that flower is my label. And so again, it's what we're taking. It's become now a great abstraction. It's no longer an image that we see as a picture. It's no longer 256 different pixels. It's now only 6 features, and we know those 6 features are a flower. And then supervised learning effectively becomes a process of using those labels in order to predict the output. I want to do a quick check for people that haven't dealt much with machine learning. Is there anybody who can explain to all of us the difference between observations, input, and features?
Okay, so the features are like your variables, x1, x2, blah, blah, blah. And then within those features, you then have your observations. Now, the features can now become an input. Remember, there was a talk about y equal to fx. So your y becomes the outcome variable, which is a function of your input variable, the x variable.
So almost correct that the features are used as the input. The only thing is the observations. So you just swapped it around. That the observations get reduced to your features, not the other way around. So the features. Embedded. Oh, I see. Okay. Yeah. It's the other way around. So you've got many observations, and you reduce the observations to features, and then the features become the input. And so it's a semantic language thing, but thank you so much for helping us clear it up. I appreciate it. And so in supervised learning, maybe actually quickly, anybody who's dealt with supervised learning, can you explain to us why we've got labels? What do we use the labels for?
Basically, if we have the labels, and we can use it to calculate an error and see how far our prediction of those inputs are. So we'll predict, see how far it is from the labeled known correct truth ground label, and then we make sure we get our accuracy closer and closer. So it allows us to evaluate our error and try and predict all the label observations in our data set correctly eventually, or as much as possible.
Exactly. So effectively, supervised learning relies on that label. It takes a prediction that comes out of that your model gives you, and it calculates, it's called the distance or the error between your label value and your prediction value. And ultimately then it becomes supervised learning is an optimization problem where you say or a minimization, optimization problem where you say, how do we minimize that error, how do we minimize that distance? Now, unsupervised learning means that we don't have any training labels, which makes that process very difficult. So effectively, the goal of unsupervised machine learning is to discover structure in the input data in the absence of training labels. So, so some of the results that we want to achieve so again, we're back to our results, problems, task framework. Some of the results that we hope to achieve with unsupervised machine learning are things like estimating the distribution of data in our input space, or reducing high-dimensionally data to lower dimensions, which we might want for visualization, or to discover groups of similar observations in data. And that specifically, that discovering groups in similar data is what we call cluster analysis. And the rest of today will be focused on cluster analysis because it's a very useful approach. And in terms of unsupervised machine learning, again, in the real world, I think there are a lot of standard results that have been around for many years that can be, when applied to new domains, I think can be very interesting. So cluster analysis overview. Again, by the colors, I hope you see that we're back to our learning framework. The results that we hope to achieve with cluster analysis are things like organizing text documents, discovering malicious genes like cancer genes, or customer segmentation. So that's typically what we want. Again, is if we had an oracle sitting somewhere that could perfectly predict which gene is malicious and which not, we don't need algorithms, but in the absence of that, they help. The problem we need to solve is how do we group the most similar objects into the same cluster? And if we start picking up on words in that particular sentence is, what does similar mean? How do we measure what similar is? And again, like how do we start evaluating? And that starts becoming really the crux that we need to solve. Cluster analysis requires us to prepare an input to define and measure similarity, to test methods and algorithms, and to evaluate our clustering that we get. And some of the skills that we need within that space is to anticipate data structure, to normalize, to choose appropriate distance measures, and to choose appropriate cluster evaluation metrics. So that's effectively what we'll speak about just now, but we're going to have a 5-minute quick working break. And the work break goes like this. Of course, I need volunteers again, as you might have anticipated. So now I need 5 people that are going to volunteer by standing up. And ideally, I want 1 person sitting in this corner, 1 person sitting in that group, 1 person sitting here, and then 2 people in the back corners. Yes, great. So what you're going to do, one after the other, you're going to tell us the following. You're going to tell us where you were born. You're going to tell us what university you're at, your age, and you're going to tell us your favorite color. Everybody else, listen well. OK, so starting at the back.
I was born in Johannesburg. My university is UKZN, Westville. What were the other 2? It's quite bad that I'm asking. What's your favorite color?
Your age and your favorite color.
My age is 23, and my favorite color is blue.
Great. OK, next person. So where you were born, university, age, and favorite color. Everybody else, listen up, because you're going to have to find the person that is most similar to you afterwards.
Cool. My name is Jade. I'm not currently at a university. I'm 29, and my favorite color is blue.
Where were you born? Johannesburg. Cool.
Hi, everyone. My name is Julius. I was born in Canada. I'm currently at UCT. I'm 24 years old, and my favorite color is also blue.
Okay, my name is Louis. My name is Louis. I was born in Johannesburg. And I'm 25. Do I have a favorite color? Let me check. Suppose blue.
Blue is favorite color. And which university are you at?
Same university.
Hi everyone, my name is Kia, like the car. I am at the University of Johannesburg. I was born in Bloemfontein and I'm 25. My favorite color is purple. Yes.
Here we had blue, 25, Johannesburg, UKZN. There we had Canada, UCT, blue, and 24. Okay, there we had Johannesburg, industry, or not at university, 29, and I didn't get the favorite color. Blue, also blue. Fudge. Okay, got such a bias. And then we had 23, Johannesburg, UKZN, and blue. Okay, so you have 2 minutes to, between these 5 people, pick the one that is most like you, and you should sit as close as you can to them. So effectively, you're going to have to take your things and shuffle the room and sit somewhere else, which I know people aren't very comfortable with. But find the closest spot you can to that person. Huh? Yeah, we just did a reshuffle. We just did some clustering. I didn't like the structure that was in the room. Okay, so now I need many volunteers because we need to figure out what just happened here. I'll start with the 2 down here. Why are you still sitting in the same place?
For me, in terms of age, I don't fit anywhere. Where I was born, I'm not fitting anywhere. Where I could find people I'm related to was on color blue, but it's not discriminative. I don't know who to go to.
So you didn't feel you should go somewhere in the middle between all of them at the intersection? Did you have a different reason for why you...
It was the same. I actually said I'm an outlier.
Okay, so we've got an outlier. I've got a question to you. Why did you move far away from that group?
No, I was thinking I kept hitting as well.
Perfect, so you came closer. Great. Anybody else? Why did you choose that? Like, who else wants to share? Why did you choose? You were sitting here earlier. Yes, I was. What makes you most similar to?
We're both born in Johannesburg.
Yes?
That's the only common thing that we have.
Only common thing. Okay, and which institution are you from? And
I'm from UCT. Yes, and I live in Cape Town. Okay. I am 32 years old, which is totally different from anyone, yeah. So that's the only thing that we have in common, just Johannesburg.
So is there anybody who moved, who had a particular strategy that they followed to move? Like how did you evaluate which of these people is most similar to you?
Most of the things were pretty different, but I had UCT and I'm at UCT, so I moved over here.
Perfect, great. So we weighted UCT quite heavily.
For me, it was a bit different. Similar age, same university, same color. And when it comes to where you were born, well, I was born in a different country than his, but it's like, I saw that most of the people here were born in South Africa, so I was like, I can relate to that.
Is this a good setup we now have in the classroom? I mean, it's different to what it was before. Is it good?
There may be other variables to consider. So on the set, it might be good, but yes. So it's maybe not the complete set of variables to form groups.
Absolutely, and so that leads to a very important question. What was my intention behind making you guys move? Was my intention for you to meet new people? And so depending on what my intention was, you might find this structure really great, or you might find that it's really shitty. And so in cluster analysis, again, in the absence of having training labels that we can use, is understanding what your intention is behind why you're creating groups is really important. So what are some of the alternative groups that could have formed? Like how else, is this the only group? Is this the only clustering that we can have? So let's keep our 4 features the same. Let's keep our 5 groups the same. Could we have arranged in a different way?
If you have ties on the variables, some of them might be more important, and especially those ties will definitely shift depending on the weights.
Absolutely. So if I had said it's most important to move to the person that likes the same color as you, you two might have found a place to sit, whereas somebody else might not have found a place to sit. And even within the arrangement that we have now, you might have still, if one person would have changed, you could have chosen a different seat, you could have chosen a different row. So there are million different ways of how we could arrange. So basically deciding, even if we knew the intention, deciding which particular of these million structures is good is really challenging. So if I wanted to create, okay, wait, no, actually. No, we'll go to that. So do you feel there's bias in the structure that we've created? Like, have I influenced how this room is shaping out? And if yes, how? Some people that haven't talked before. What about the front row? You guys have gotten off lightly. You don't feel, okay, that's fine. Anybody else? Is there bias in the structure?
Number of groups that we had to choose initially. Yeah. And I think, I'm not sure about that one, but the first people were in the group. I think it also had an influence on how we cluster.
Yes. So the 5 people we chose as the initial people, they influenced, absolutely. So if I had told you that my intention behind creating these groups was to find the best neighbor, like people that would make the best neighborhoods in a retirement home, would this have worked with the people in the room? But I selected age, and I mean retirement home age should be fine. There's a problem, but what's the problem? Absolutely. So we've got mostly young people here. So if I wanted to find like clusters of people going to old age homes, this just wouldn't be a good data set to use. And so effectively, we've now mentioned a whole bunch of different things that have prejudiced how this grouping is formed, from my intention to the people that we selected as the initial nodes, to the features that I selected of how to arrange, and to ultimately the people that are actually present in this room. And all of that determines what we can get out as a clustering structure, and whether the structure that we get is actually any good for answering the questions that we're interested in. So coming back to cluster analysis, ultimately, clustering algorithms give you clusters, whether you like it or not. So if you use a clustering algorithm and you get clusters out of it, you shouldn't be surprised. You haven't done something great. It's just done what it's been designed for. So effectively, if you use an algorithm, again, like if you use a clustering algorithm and you, and you get a clustering structure, let me say it once more, it's not magic, it's what it's supposed to do. Therefore, circles, and clustering them seems like, at face value, clustering seems really easy. It's like, okay, cool, we'll group the 2 that have the similar color. Makes sense. But in reality, this grouping is equally possible. So if we don't have, if we don't have labels that tell us which was good or which was not good, it becomes inherently difficult and ambiguous. Yeah, so effectively, there are always many different possibilities of clustering, which makes clustering inherently ambiguous. In order to even start having good clusters, we need to define what we mean by similarity. So and the different ways of, or the different definitions of similarity. And so again, are we saying we're looking for similarity by age? Are we looking for similarity by color? Are we looking for similarity by university? And once we've defined our similarity, we then choose a distance measure, and even the distance measure biases the clustering structures we get out. So a very common distance measure is Euclidean distance, but Euclidean distance inherently creates round clusters. So if the structure in your data, the clusters aren't naturally spherical, then using Euclidean distance as a distance measure is going to give you, it'll give you spherical clusters, whether you like it or not. And so again, it's having an initial understanding of what structure pre-exists in your data is really important to get clustering results that are going to be sensible. Are there any questions on this? I feel the movement exercise maybe illustrated the point, but is there anybody who's got a question on the importance of data, on maybe what structure even means? Structure as a word was mentioned a lot in the previous lectures. Is there anybody who feels uncomfortable with the word structure?
In regards to unsupervised learning, I'm assuming then we don't have a label. We don't have like our end goal. So how then do we know how to, which labels to use, not which labels, which characteristics to choose between this data set that we have so that we put them in a similar set if we don't know what to look for?
Absolutely. So I'll get to some approaches for doing it a little bit later. But to start building it up again as an argument, as a starting point, it's important to have an intention behind what you're wanting to cluster for. So it is that knowledge, am I clustering to find residential neighborhoods for an old age home? Am I clustering to find people that want to go on holiday together? Am I clustering for any other reason? So without that intention, we actually can't evaluate in the absence of labels because we don't have anything to label against. Once we have that intention, I can then later say are the clusters that I have, do they meet my expectation for meeting that intention. So I could then say, for example, at a later stage, okay, it's difficult in a real world example, but let's say I were to group by clusters of people that are likely to go on holiday together. I could at a later stage go and ask everybody, with whom in the room did you go on holiday? And then I could check, are the groups that people went on holiday with, do they correspond to the clusters that I created? So those then become evaluation measures. But again, why is the intention important? Because if I say, did people go on holiday together, but I actually wanted to do these old age home neighborhoods, I can't actually compare. It's like comparing apples with bananas kind of thing. So as a starting point, effectively, it's about, initially when we say is how do we choose the similarity between one, call it an object, so an object or a pattern together with its centroid, so kind of the closest point, the center point of the cluster. We want to say is what does similarity mean between an object and the cluster center? And how do we then calculate, what distance metric do we use to calculate the difference or the error between them? And that effectively is what a lot of clustering comes to. The two most commonly used clustering groups of clustering algorithms are partitional clustering and hierarchical clustering. And I'll go through both of them in a little bit more detail that you can start getting an idea for it. Again, I've not put code because these are simple algorithms that have been around for several decades, and you will be able to find the actual implementations of them you can find online really easily. But what I rather want you to have is this kind of the sense of saying, how do I know that this was a good approach, and how do I evaluate it? So in terms of partitional clustering, the most common ones are k-means, k-medoids, and k-medians. K-medoids is effectively what we did now. It was one where I pre-selected 5 people within the room. You then said, we defined features of those 5 people. You would have, in your mind, assessed well or not so well what the difference was between you and that person, and you moved towards them. Now, we missed out the next step, which would be one of saying, within your group now, let's reevaluate what the mean is of all the different characteristics that you have. So you might find that everybody, or I guess mean in this case is difficult because it was categorical data, but you might say that the majority of people in our group actually, like, we're from Johannesburg, they're working in industry, they over 20, like their average age is actually 33, and in terms of color, like, I don't know, like color was like blue. Okay, it was blue, easy, fair enough. And then we'd say, okay, great, that's the new centroid. So what we then say is, great, put up like the virtual centroid of that group, put out what your characteristics are, and then let's repeat this whole reshuffle exercise. And effectively, we do it again and again and again until we start finding that the groups don't change. So that's k-medoid. K-means, which I've written out there, is the same, except that we would have selected not from people in the group, we would have selected just 5 virtual center points. So I could have said, yellow, Johannesburg, UKZN, and 21, go to the back. Purple, Pretoria, UCT, and I don't know, purple, Pretoria, UCT, oh, and 33, go to the front. And effectively, then you would have decided in these virtual centroids which one is most similar to you. But again, it would be a similar process. So we'd start off by selecting, these are clusters, then forming the clusters by moving the individual objects or patterns as close to the centroid as possible, recomputing the centroid, and repeating it until we get to having the same results. K-medians, instead of computing the average in the group, the average distance, it computes the median distance. So again, it's the same concept. Principally, is there anybody who's got a question about this reshuffling approach? No? Okay, great. If we then move on to hierarchical clustering has got 2 strategies. It's got agglomerative and a divisive are the 2 most common ones. And agglomerative is effectively a bottom-up approach. Divisive is a top-down approach. So what we could have done is we could have had everybody in the room say, these are my 4 characteristics. Based on that, actually, wait, that was a bit the approach that you were saying. So you speak to your neighbor, you check if your neighbor's got the same. If you're the same, you stay together. If not, you move apart. And then you keep doing that, building up until you find your most similar groups. Or top down, we could have said, okay, everybody who's from Johannesburg in one side, everybody who's not from Johannesburg on the other side. And then within that, everybody who likes blue, everybody who doesn't like blue. So effectively, we could have broken up into that. Now with both, actually, hierarchical. So then hierarchical clustering has got different ways of defining distance or similarity. So there's a single linkage criterion, which speaks to within your group. So it comes back to the minimum distance, which, again, in categorical data is a difficult measure to use. But what we could say is between all the ages in your group, what are the closest two ages? That would be our single linkage criterion. If we have a complete linkage criterion, we'd say, what is the biggest difference between the ages? And the average linkage criterion would be within your group, what's the average difference? So effectively, you can choose from so now you're saying we want to start clustering. What do we use? We can do partitional clustering, or we can do hierarchical clustering. If we do hierarchical clustering, we can do this agglomerative or divisive. Within that, we can look at each of those different distance or similarity measures. So already now we've got 2 times 3, so we've got 6, and then we've got another 2 on the another 3 approaches. Now we've got 9 different things that we could try that are going to give us potentially vastly different clustering structures. Both with the hierarchical clustering and with the partitional clustering, what we haven't yet spoken about is this initial choice of 5. So 5 was a random number. We could have had 3 clusters, and it would have ended completely different. So not only is the challenge of saying, are the clusters good, there's also a question of why did we start with 5? What is the best number of clusters? In hierarchical clustering, you typically choose what they call a stopping criterion. So you say beforehand, at some point, we just say timeout, overs. And again, the approaches, typically it's often used by visual inspection. It's called an elbow method. You kind of start checking when do your metrics, when does your error become large, and there's a point where you say, that was it. I want to get to the evaluation part, which will then, I think, make the stopping criterion more clear. So the big question is, what is a good clustering structure? There are many potentially, but there are ways in which we can figure out which are better and which are worse. So firstly, we need to look at the clustering tendency of data. So that is saying, is there structure inherent in the data? And if yes, we don't really want to find surprises. We want to find what exists already. Then we need to evaluate whether the number of clusters that we've selected is good. And finally, we need to see if the cluster quality itself is good. And I think some of this morning's lecture actually in some ways is applicable here, that so 2 clusters, for example, often gives very good results by metrics only. And that's because you'll have one cluster that has got almost everything and one cluster that's got very little. If you don't go and look at your clusters, you might be like, oh yes, awesome, 2 clusters is the best, the best structure. But not necessarily. So it's worth exploring a wide variety of different numbers of clusters before settling on one. I'm going to speak mostly to cluster quality. So a valid cluster is a cluster that's unusually compact and unusually distinct. The challenge is knowing what unusual means and finding effectively a baseline against which unusual has got meaning. I quickly want to do a time check. Oh, I've got 2 minutes. Fantastic. I didn't think I'd be able to talk for an hour. Who would have thought? So compact, as the image shows, compact means that the patterns in an individual cluster lie close together, whereas distinct means that your clusters are far apart. So, for example, having the lady sitting at the front here is making her cluster less compact because she's removed herself from it. So effectively, that cluster there is a bit less compact. Whereas distinctness, I guess, maybe, again, is like these middle clusters here are not very distinct because it seems like there's a lot of overlap and a lot of merging. But those are the 2 things you typically want to assess. The upsetting part about the metrics is they often either measure compactness or distinctness, and often clustering structures that get very good results for being compact are actually don't get good results for being distinct, and vice versa. Which is, okay, which is a feature of the metrics and of one metric usually not being enough to assess it all. So effectively, what we want to assess in an evaluation process is how well does the clustering structure represent the structure of the data? Because we're not out to find new insights, you're out to discover you might be out to discover new insights, but we're not out to discover something that doesn't exist. And so there are three different approaches that we can take, and let's start speaking to your question. We can have external metrics, internal metrics, and relative metrics. External metrics implies that you actually do have a set of labels that you can compare against. So if we did actually know what the real clustering structure was supposed to be, we can compare the structure that we got in unsupervised learning against that real structure. If we don't have those labels, we effectively have to compare the data with itself. And what becomes challenging there is that the actual figure value, the numeric value you get out of a metric is essentially meaningless. Like, is 10.3 good? I don't know. It's a random number. And so because of that, relative metrics are often used then ultimately where it says, I might not know if 10.3 is good, but I do know that 10.3 is better than 11.4 if 0 is my best value. And so quite often then, having a relative evaluation is really the way to go. So one metric is seldom good enough I said never enough, okay, good. One metric alone is never good enough to evaluate a clustering structure. So the best is really to try numerous different clustering algorithms and to have numerous different clustering metrics that you use. And based on that, then you kind of have to start like looking what metrics do you get, how do they perform, what do your actual structures look like. It's unfortunately like a bit of a messier process than what supervised learning is. So some of the common metrics, just to get you started when you look it up, is Davis-Billden index is used often, mean index adequacy is used often, silhouette index is used often, and if you Google clustering metrics, you'll find a whole bunch. And so typically using a lot of them together and finding ways of mashing them up, maybe mashing them up nicely, is likely to give you, in the long run, more accurate results than if you rely on a single one. And so, to leave you with, I've got an ML application success algorithm. So firstly, if you live in an environment in unsupervised machine learning where you need to try so many different things in order to come to a structure where you inherently don't know up front whether it's going to be good or bad, it's important that you standardize your process. So you need to have a standard approach to how you do experiments. You need to systematically try different things. So you need to know what you're changing from one to the next. Because only once you're systematic about the process of changing things, you can actually start to automate it and try everything, or as close to everything as you can. You need to have a robust process for comparison, because if you've got 150 different things that you're going to look at the end of the day, you need to know how do I compare them. And then as a final thing is you want to learn from your mistakes and improve. And so if you apply this infinitely often until you get better and better and better, you'll probably eventually converge to being excellent at unsupervised machine learning. That's it from me. Thank you.
So in my case, the issue that I have is with deciding whether it's supervised or unsupervised learning. Yes, it's obviously depending on the project that you have. So in my case, my current project is more from sort of like I have a list of questions where I ask people about the service that is delivered by government. Now I'm not sure whether I'm using supervised or unsupervised learning. That becomes an issue.
So the responses really depends on which question you want to answer. So for example, you might say is which people have similar questions. So which people have similar responses? So kind of is there similarity between, like based on the words that people have used? Are there particular groupings? And you might not know up front what those groupings are. Then you would want to use unsupervised machine learning. So again, like you might say, like I don't know that much about text because I've mostly been working with time series data. But you might take the responses that people have written and segment it into many different words. And based on the words, you might group people's responses into groups. That would be unsupervised learning. Supervised learning, does anybody have an example for a supervised approach? No, yes. I'd have to think a little bit, because my mind is now in the supervised space. But if you, like, a different problem might require for you to use supervised. So it really depends on the question that you want to have answered.